Look at the drain current of M5, first of all, M5, M1, M2. I think it is working properly because at least I can see the DC voltages are proper. Why are you running transient? I don't need transient, just DC operating. You can use the probe, right? So the probe will tell you what is the DC current and DC voltages. There is a probe for current and voltages, right? So if you look at, I think tools, within tools, I think you have some option for probe. There was not here, so simulate somewhere there was a probe option where voltages and currents. So I think you could have put a resistor also over there, 1 ohm, 0.1 ohm, whatever. That will also tell you. So DC operating point, I think click at .op. It should be able to like give you the current. It should print the currents also to different branches.
So is this visible? So like
ID5 is 998 micro.
98. Yes.
So that is okay. That is 100 micro. It is a 98 micro, so very close. So that is not a problem. Look at the M1, M2, ID1, ID2.
M1, M2. So the
ID1 is 45 micro. Another ID2 is also 45 micro, which is also correct.
50,
I
53 micro.
no
Yeah.
ID is ID M1 is 45.4 micro, which is okay, and ID
M2.
2 is also ID2. I can see where is ID2. ID2 is also
53.
52. So this is ID2 is 52 micro, and this is slightly lower. So why? Because again, this is a not a very high gain stage, so you are getting some error. So the voltage will not be exactly equal, but close. So look at the DC voltage. What is the DC voltage? So you are getting V3.9 volt, and the other voltage is settling to 0.89, which is okay. Means it is 10 millivolt error. 10 millivolt error means your gain is not too high. So overall, in the closed loop, you are getting a 10 millivolt error. That means your overall, gain is 100 around, because 1% error in closed loop means close to 100 gain. So you may have a chance to increase the gain. So DC point of view, I don't see much problem. DC point of view, the DC voltages are correct. So you can see that the input voltages are very close together. They will become more close if your gain is higher. Right now the gain is relatively lower. Therefore, you have the voltages showing some error. That's why I had asked you to notify the error also. So if your gain is poorer, your error will be larger. As you increase the gain, the error will disappear. So now let us look at the so is this clear to everyone? So you can see the current, the DC current is coming properly. DC node voltages are also proper. The transistors, M1, M2, if you look at it, the M1, M2 drain voltages are 1.33, which is as compared to gate voltages higher. Therefore, there is no problem with the saturation region. They are very much in saturation. Tail current source also, if you see, VG is 0.6 volt and the drain voltage is 0.53. So that is also in saturation without any problem. And the currents are mirrored properly. Right now, you are getting some, you are having in the feedback loop, you are seeing that there is some error. It is not exactly coming same, but the resistor is at least enforcing that the DC values are almost similar. Now, at this particular point, we can try to look at the AC analysis and figure out what is the frequency response. So just let us look at the frequency response. You can make the R even larger. That will become even more ideal, because right now the only purpose of R is to get a DC biasing. That's all. So that is just.
So this sort of graph is coming like.
Okay, so the R is so you can increase the R value. Let us see. So just so this is uh, for the open loop case, you can maybe you can make it 10G also. You are getting, so you are seeing 1 kilohertz is a band pass kind of response coming. So the R basically it is introducing a band pass response, and that is because at this R along with the capacitor, the parasitic capacitance of the MOSFET, it basically creates a band pass response. So apart from the low pass filter response that you get because of the MOSFETs, MOSFETs capacitance, this R and C of the MOSFETs, like if you just go to the circuit. So this circuit, if you see between, if you look at the closed loop response, actually this R is also basically having the parasitic capacitance associated. At the output node, you have parasitic capacitance. At the input node, also you have the parasitic capacitances. And if you look at the open loop response, uh, so it has basically uh, high pass characteristics because of the RC filtering effect. So if you look at the feedback topology, what kind of feedback it is, we are sensing the voltage from the output and we are feeding back voltage. So it is a voltage feedback. So when you have to sense the voltage, it is shunt at the output, and when you feed back the voltage, it is series at the input. So that right now, the thing is that we have not covered the feedback topologies, the 4 type topologies of feedback, and how to identify the feedback, how to open the loop. But here, at least you can see that this is a voltage feedback. Output is voltage. That means we are sensing a voltage, and also the input side feedback is we are returning the voltage. We are basically subtracting the feedback voltage from the input because it's a differential amplifier. The input side, we are just having the feedback voltage at the negative terminal, which is subtracting from the input voltage. So it is a voltage feedback, voltage feedback, voltage sensing, voltage feedback. And that basically means when you have to sense the voltage at the output, it is shunt, and at the input, it is basically series. Now, in order to, uh, for the time being, I would say, let us, for the time being, you just understand. We will do the detailed analysis of this after going through the, feedback theory. But for the time being, you can understand that this high pass filtering effect is coming because of the parasitic capacitance and the R1 forming a high pass response characteristics. So we will look at that once we understand the loop opening and how to analyze the feedback. If for the time being, you can, if you want to suppress that band pass behavior, you can make it even larger, make it 10 to the power of 11 or 10 to the power of 12. That is also okay. You make it 12 to the power of 12. So if you make it higher than the low pass pole that you are getting, sorry, the high pass pole that you are getting, it will shift towards further lower frequency, and it will basically become more kind of a broader band. So now you can see so this one, you can see at least the band pass characteristics becoming broader, and you have basically the low frequency pole, low frequency, a response flat up to 1 kilohertz. So we are interested in the band, so the flat band characteristics. So resistor has only introduced this high pass characteristics in an artificial way because we are actually not having this resistor. It is just for the purpose of emulating the uh, DC biasing and ensuring that output bias is proper. That's all. So now we can just ignore this, high pass characteristic that is coming at low frequency and look at the high frequency pole and uh, the mid band gain. So let us see what is the mid band gain. Mid band gain is coming around, if you see, so input output mid band gain is not very high. You are seeing only around 27 dB, 20, yeah, so 23 dB, which is not good. This is just around 10 to 15. So can you just check the two stage gain, the first stage gain and the second stage gain? Separately, you can look at the first and the second stage gain. So first stage gain, it seems like we are getting negative, and that is very surprising. Why we are getting negative, we need to see that.
There.
Yes.
Sir, here we are doing this analysis for the closed loop, no? So our gain will be less
No, no, no.
only.
This is not closed loop. This is the R value is too high, right? So we are not. This R is only for providing the DC bias. So that is the mid-band frequency response. It does not affect so much. So that should be okay. So here, what we are seeing is um, the mid-band gain should not have affected so much. So what you can do is you can whatever DC bias you are getting right now. For example, you are getting a for after connecting this R, whatever DC bias you are getting. Just for example, right now you're getting 0.891, and the other input you are getting at is 0.9. So you can connect this DC voltage of exactly this value 0.89134 and then disconnect the resistor. So that will basically get rid of the resistor, and then we can look at the open loop response. That is just going to help us in getting the appropriate DC bias. So just put the exact, not at the output, input. In output you can't put this, right? So output you have to check the response. Input you can put so that we have appropriate DC at the output. So we want to establish appropriate DC at the output and then check the closed loop response. For that, we will just check. We will just keep that same DC voltage at the input, which is producing that required DC at the output, so that the output is DC biased properly. We know that this particular amplifier stage, the DC bias is not stable unless you have a feedback operation. So in order to observe the open loop response, one possibility is that you just uh, why have you where no, 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 what are you doing? I told you to put this DC on the other side. This side it was 0.9, right? So you have to see what we are doing. We are first we saw that okay, with this exact value of 0.89 whatever was coming at the other input, the output was at proper DC bias. So we will put that DC at the same second input, not at the first input. First input is 0.9. So we are just emulating the same condition, same DC bias condition. So if all we want is that the output DC should be at the proper value. So we can see so now once again you can see that is coming at proper value. The output DC is 0.89, which was also there during the feedback. So now we have with this trick we just have established the appropriate DC bias. We just observe that okay, what is the DC required at the other input to get a, 0.9 volt, almost 0.9 volt uh, uh, output at the second stage. So that is okay. Now you can look at the AC response. So now this will not have interference of the resistor. So we have got rid of the resistor just to uh, that low high frequency, the low pass response that we are getting. Sorry, that high pass response that we were getting, that is gone. That was because of the resistor. We still see the gain is poor. So the gain is still around 35 dB from input to output, and the first stage gain, I think it is the blue curve. So
The
which is the
green one,
first
first
green
stage.
one? Green one, that means your GM2 is not proper. So green one is showing that the first stage gain is still low. So we need to figure out. Let us see what is the. So since we have got rid of the R, so that is also changing the gain magnitude a little bit because R also has some loading effect. So remember, this R we have put only for the purpose of getting a DC bias for our open loop analysis. There is no other purpose. It is an artificial imposition. So we have got rid of the R and just imposed the right DC value with which we are getting a proper DC at the output. This is not the actual way in which we can bias the circuit. This is just to simulate the open loop condition. That's all. Now let us look at the so first stage. What is the W by L of M4 that you have? M4, M3.
So these are kept the same as given in the teams, like 5 micro by 180 nano.
Okay, so it seems like we will. Uh, so let us. We will have to make it weaker because right now it seems, or you can what you can do is input side anyway you have large W by L. So the GM by GM1 by GM2 gain should have been good, but so far we are getting.
So M1, M2 VGS is less than V threshold in this case.
The current is proper, right? So the what we are interested in, so it is close to subthreshold region. It is not exactly in super threshold region, but still, the gain will be governed by the W by L ratios. So what we can do is you can let us try to increase the current to 0.2. That will basically avoid the subthreshold region operation. No, increase the reference current. You don't change the W by L because other ratios are determined according to that. If you change the W by L, other things also need to be changed. So I have given you some ratios considering some current distribution.
Sir, we can
if you
change
remember
the L
the
because that will increase our.
That is okay, but you remember that there is a relationship between the currents in this case, right? So if you change the DC bias current in one branch, the other branches, the DC bias will get affected immediately. So if you look at the, I don't think I have annotation issue here. Can we annotate anything? No, right? Annotation is not there. No. But anyway, so what you have is, that is the problem. This tool doesn't have annotation. Otherwise, I could draw something somewhere. This one, no. No. So here, see, the moment you change the DC bias current, and here you have the DC point of the output also has shifted because increasing the current means you are lowering the DC potential of the drain of M4, M3. VSG has increased. So definitely you are now going to get larger, current flowing through the PMOSs on the output side because their VSG has increased. But now why the output DC point has increased? Because on the lower side, if you see the M9, if you look at the M9, that is still trying to supply the same current because there the W by L has not changed, but VSG of M8 has increased, right? So VGS of M9 is remaining same, but you have increased the VSG of the M8. Why it has increased? Because the VSG of, because we have basically increased the current, and as a result the VSG of M4, M3 has increased, and that is forcing the increase of VSG of M8. Now in order to maintain the same current provided by M9, because the current in M9 is trying to remain same, in order to support the same current, the VDS of M9 must increase, right? So therefore the drain voltage is going up. So if you don't take care of the DC biasing, if you just keep on increasing the bias current in the first stage, eventually the output voltage will keep going up. So that, of course, we have to stop at a certain point. Still, at this point also, we are at proper DC bias. Output 1 volt is okay because VDD is 1.8 volts. So we are still close to midway. So we are okay. Right now also, if you see the VGS of M1, M2 are quite okay, 0.89 and 0.495. So we are having around 0.4 volt of, so just close to actually VT. And then you also have basically the VSB of this PMOS, this NMOS you have shorted. If you want, you can keep the body to the ground also. That will have slightly higher threshold voltage. Right now, the threshold voltage is, of course, not having body effect. The moment you connect it to ground, it will be having higher threshold voltage. Now we need to see if you look at the if you want to have larger gain in the first stage, the only option is that we increase the uh, GM of M1, M2 or reduce the GM of M3, M4. But remember here, we are not actually concerned with the gain from the first stage. So the first stage is only providing a good common mode ejection ratio, and it is providing small signal current which is going to the output stage. So the most of the gain will actually come from the output stage, which is right now pretty small, right? So you can see that the gain right now it is only around 35 dB, which means just around 15-20 kind of gain you are getting. So in order to improve the gain, we can rely on the second stage, which is the output stage, and try to basically increase the RO of that stage to get a better gain, because first stage is anyway in this particular topology is not responsible for getting voltage gain. It is just basically providing a good common mode rejection, and it is basically routing the small signal current to the second stage. That's what we have studied. So let us try to once again you try to get the board plot, and we will try to then increase the gain of the second stage, and then that will also improve the error. So it is again same around 35 dB. So now in order to increase the gain of the second stage, one option that we have is we can just increase the RO of that stage. So let us try to increase the channel length of the output stage, and as well as the input GM we need to keep. So input side you can so let us so here what will happen is if you increase the channel length alone, uh, so as a result the current mirroring that is happening between M4 and M8, now M8 will have smaller amount of current. Likewise the mirroring that is having between M7 and M9 will also have smaller amount of current. So we have to make sure that the ratio by which we are increasing M8 and M9 is same. The ratio of increase should be same, so that their currents are scaling up by same amount or scaling down by same amount. If you change that ratio, then what will happen? The current mirroring ratio between M8 and the M3, M4. So M8 and M4, whatever current mirror ratio was there, and whatever current mirror ratio was there between M7 and M9, that was supposed to provide equal current between M8 and M9. So ideally, under DC condition, M8 and M9 are sized such that they carry equal DC current. So while so let me describe certain things, and then you do the change. No, so I asked you to only increase the length, right? So you're making changes very quickly without listening. So let us. So what is the W by L you have kept right now? For the two devices, what is the W by L? M8, M9?
So I've kept it the same ratio. I've just doubled each of the values.
No, for what? So only M8, M9 or what?
For M6, M7, M8, and M9.
Okay, so so now you see that overall we have basically increased the channel length for the output stage, and also M6 and M7 has been basically sized up in the same manner. The channel length has been increased in the same manner. So earlier DC condition point of view, if you remember, the bias current M5 was double that of the bias current provided in the output stages. Basically, whatever was the uh, whatever was the bias current in M3 and M4, of course, double that is flowing in M5. And then the ratio of M6 and M8 in the beginning, we had almost double. So W by L was double. W was 4 times and L was twice, as far as I remember. So that means the M6 and M8 were designed or sized to have double the current as compared to M3 and M4. And likewise, M7 and M9 will also be sized, because they will also be sized to carry double the current. So that will be ensured, because whatever current is mirrored in M6, the same flows in M7, and M7 and M9 are also having the same ratio. Therefore, the same current will be coming in M9. So DC point of view, initially we had twice DC current in M6 and M8 as compared to the DC current in M3 and M4. Now, in order to increase the gain, we have increased the channel length of these 4 transistors. That means the RO of the output stage has gone up. That should boost up the gain to some extent. Whatever is the length root under that will go up. So right now we are expecting maybe just 3 dB. So you have increased the L only by root 2. So that may be 3 dB increase in the gain. So let us see whether it is touching 40 dB. What is the gain right now? So 36, earlier it was 35, so it has 37 dB. So 3 dB kind of improvement you are getting in the output stage. So now you can, in order to increase the gain further, we can also try to increase the GM of the first stage. So let us try to increase the W by L of the input device so that our GM, because remember in the stage 1 contributes the GM and stage 2 contributes the RO. In order to increase the gain, these are the two knobs we have. Increase the W by L of M1 increases the GM, and also the bias current, if you increase for the first stage, that will also increase the GM. And the second stage, we have to increase the RO. So first stage, W by L of M1, M2 you can increase, and also bias current you can increase. That will increase the GM of the first stage, and the gain needs good GM at the first stage and good RO at the second, the output stage. So let us right now, let us try to increase the W by L of M1, M2. What is the so right now it is 20 micro, I think. So you can just make it maybe 35 micro, or make it 40 micro, doesn't matter. 40, it's okay. Yeah. So this will again give you another 3 dB. And finally, this will also make sure that when you are connecting it in a voltage feedback, voltage follower configuration, it will also have lesser error as the gain increases. We also need to make sure that if your output is going into triode region, voltage is going too high, we will have to again. So see, now the output DC potential is going upward. Why it is going upward? Because bias current has been increased in the first stage. So go to the circuit, remove this plot. So while we are making changes, we should understand what is happening in the circuit. So now, right now you see the bias current in the first stage has been increased, and that basically means that the VSG of M3 and M4. So if you look at the VSG of M3, M4, that is continuously increasing. As the bias current is increased, now the VSG is almost 0.7 volt, right? So if this is a 0.7 volt, that means once again for the output stage, the VSG of M8 has increased to 0.7 volt almost. And whereas the VSG or the VGS of M9 is remaining same. So following the same argument, now in order to basically support the same current, the VSG, sorry, the VSD of M8 must reduce and VSD of M9 must increase, because now you are going on increasing the VSG of M8 while trying to maintain the same current in M8 with the help of M9. So M9 role is what? M9 is a current source. Its role is to maintain the current given by the M7 branch. So now, in order to ensure that our DC point is proper, we may again change the input DC level slightly. So we can see that the V4, what direction we need to increase or decrease, so that my output DC comes back to a lower value. So what is the relation? This is the inverting input, right? So in order to basically, in order to reduce the voltage at the output, I need to increase the inverting input. So maybe I can keep it 0.9, 0.91 something. So increase it slightly 0.91, so that it again goes back to the midpoint almost. Oh, so it went too high. So reduce it, make it 0.9. Again, still it is low. So maybe a little bit, we need to reduce it further. So little bit more. So this is just, so remember that this technique that we are doing, iteratively finding out the DC bias, is just for the sake of our open loop analysis, nothing else. Yeah, so this is okay. Now we have again come back to appropriate DC bias point at the output. This is just to ensure that all the transistors are remaining in saturation. Remember, in this amplifier, the output stage is not having a stable DC bias unless it is connected in feedback. So just in the open loop circuit, we are simulating it just to get the open loop gain, and therefore we are just sweeping the input DC to figure out what is the DC point. That's all. So in the actual scenario, we will always be using feedback, and in that case, it will not basically be, we will automatically get the required DC at the output. Whatever is the DC at the input, that will decide the DC at the output. So now you can figure out what is the gain once again, frequency response. Now you can see once, let us look at the frequency response first. The bandwidth will also reduce. So now we can see it is coming close to 40 dB, 39.6, so almost 40 dB. 40 dB means a gain of 100. So a gain of 100 has been achieved in this particular stage. Now, likewise, if you want to increase further, we can, so look at the bandwidth also. You have to take note of the bandwidth. Bandwidth right now is around 10 megahertz to 100 megahertz, around 100 megahertz. That's what it looks like. 100 to, within that. So yeah, 33 megahertz. Okay. So as you increase the gain, bandwidth will definitely come down. And approximately, we can also see what is the dB, what is the fall. So in 1 decade, how much it is falling. So if you keep the cursor at the frequency, say 100 megahertz and 1 gigahertz, you can see what is the slope, how much dB it has fallen. 100 megahertz, if you see 30 dB, and 1 gigahertz, let us see, almost 18, how much it is? 4 dB. No, yeah, so it is 4 dB. So 4 dB, so 20, how much was earlier value? 20, for 20, 100 megahertz, it was 29 dB, and there it is 4 dB, so 20 dB, right? So almost like slightly higher than 20 dB. That means the second pole is approaching. So it is slightly, the fall is slightly higher than 20 dB per decade. So that means at higher frequencies, more poles and zeros will be approaching. But if you look at 0 dB point, let us see where is the 0 dB point. We can also look at the phase margin, right? So let us see what is the 0 dB point. So 0 dB point, if you see the gain, where the gain is 0 dB, let us look at the phase. So this frequency, if you see 0 dB point is coming at frequency of 1.4 gigahertz. So that 1.4 gigahertz, what is the phase? Let us see.
So minus 175, minus 176 degrees.
Yeah, so minus 176 degree. That means it is not having enough phase margin, just 5 degree, right? So we will, need to basically have a either some compensation technique to have better phase margin. So for compensation, that's why I asked you to that we can use a capacitance of some decent value at the output. So that capacitance will basically push the dominant pole further down. So that just needs to be connected at the output, between output and ground. What are you doing? Just one capacitor between output and ground. So I hope you understand, right? So we are able to see the phase margin. It is not enough. So at the earlier we were getting around 10 millivolt of more than 10 millivolt of error. Now the gain has been increased. Earlier the gain was just around 25, 30. Now it has been increased to say 100. So the error should also reduce to 3-4 millivolt at max. What is the C value you have kept? So this C value, remember, it will just push the first pole down, and therefore it may increase the phase margin. What is the C value?
So first pole down is if we connect them across, right? Then we have that Miller multiplication.
This stage is not for Miller multiplication, right? So this output first stage is not having. So if you look at the dominant pole, you can do Miller multiplication also. So here the thing is that it is not a symmetric structure, right? So you have, if you look at the overall, dominant pole, that is the first one is the dominant pole. The output node is the dominant pole. Here, the impedance at the first stage output is very low. So if you use Miller multiplication over there, that will not give you a dominant pole because the impedance over there is low. So the Miller multiplication is used when you have high impedance at the first stage output also. That will be applicable when you have a current source load at the first stage. Right now, this impedance will be pretty low because it is a diode connected. So if the second stage will give you Miller multiplication, no doubt, but as a result, whatever capacitance you get at the output of the first stage, that will be multiplied with what? The pole will be determined by that capacitance, Miller multiplied capacitance, and the RO at that point. Whatever the RO, what is the RO at that, or what is the output impedance of the first stage? Is low. It is GM only, 1 upon GM. Therefore, it will not give you dominant pole. Rather than in this case, because the output node itself is the only high impedance node. Remember, in this circuit, we had discussed that the only high impedance dominant pole in this case, only high impedance node is the output node. Others are all low impedance node. Therefore, we already have a dominant pole. We just need to push it further down. That's why we can keep a sufficiently large capacitance at the output pole directly. Miller multiplication will not work in this case because the Miller multiplication works because in case you have the first stage having higher impedance. First, in that case only, after Miller multiplication, you will get a dominant pole at the output of the first stage. Here it will not happen. Now let us look at the what is the 1 pico. 1 pico is also quite large, so let us see. 1 pico will push down the bandwidth, but let's see. So the bandwidth will be limited, but the phase margin may be improved. Let us see the phase response and the magnitude response. So we may need to iteratively change this C1 to arrive at a better whatever is the required phase margin. So right now, let us see. So the gain, low frequency gain remains same. High frequency, you can see the 3 dB point has gone down. It is almost now below even 10 megahertz. So just few megahertz of 3 dB frequency. So 3 dB is coming around. You can see almost just around 3 megahertz. And now you can see the 0 dB point. 0 dB point is 0 dB point. Look at the 0 dB point is coming at this is your 200 megahertz, and for 200 megahertz, what is the phase? Phase is 124.
5 degrees. So now we have
right. So 125, 125. So this is pretty safe, right? So we have more than 55 degree of phase margin, which is quite okay in this case. So here you may have a option of reducing the capacitance a little bit rather than keeping 1 picofarad. We can go for slightly lower capacitance. Still, we will get not 0.2. Let us give it 0.3 at least. So iteratively, we have to arrive at that capacitance so that we have a required phase margin, and at the same time we have a desired bandwidth also.
now it's around 6.5 megahertz.
Yeah, so now the phase margin is almost you can see now it is 35 degrees. So at 0 dB point, you're getting around 146. So it's 35 degrees. The phase margin has reduced 35 degrees. So you can understand that by adjusting a little bit, you can go to 45 degrees. And once again, you understand the reason why we keep a good phase margin, because if you, because there are variation effects, whatever phase margin you are setting in the actual design, after fabrication, you may get a different phase margin. It may, in fact, end up violating your phase margin. Therefore, we, considering the variation effects of the actual circuits, we should also keep a good margin. So earlier value was safe because of, although the bandwidth was lower, but phase margin was good. So we can keep that value also. Now, I hope you understand the direction, right? If you have to increase the gain further, what are the things we can do? You can increase the W by L of the first stage, that the input device, and also you can increase the bias current of the first stage. For the second stage, you have to reduce the bias current and also increase the L so that you can basically get a larger RO. So that way we get a good GM from the first stage, good RO from the second stage. So this is the principle of this particular topology. And also we saw that, okay, dominant pole is at the output of the second stage. First stage is having low impedance node, therefore it is not contributing significantly to the dominant pole. Only the second stage is having high impedance node. Therefore, intentionally we added more capacitance at the output of the second stage to push the dominant pole further low and hence improve the phase margin. Now you can basically look at the closed loop response. You can connect it in the voltage feedback, unity feedback configuration, and look at the error resulting from that. Remove the DC at the DC before you remove.
Yes, sir.
No, V4 you have to remove. Have you, what have you done to V4?
I removed it.
And input DC is at 0.9. So still, it seems the gain, the difference is pretty large. And that is because if you see under this condition, your, yeah, so the output, yeah, so what, how did it change? So now automatically, yeah, so now you can see that the 5 millivolts. So as I mentioned earlier, it was around 10 to 12 millivolt. Now it has reduced to say 4 millivolt. That's what we expected, right? So we increased the gain almost by a factor of 3 to 4. So the error has also reduced by a factor of 3 to 4. So that is a straight relationship between the open loop gain and the error that you get in the closed loop, right? So that is what we are seeing. And now you can also check the closed loop bandwidth. So input to output, what is the closed loop bandwidth?
Should I remove the capacitance or I keep it?
No, no, we'll keep it because ultimately the capacitance is for stability of the loop, right? So we don't remove the capacitance. Capacitance is supposed to be there for stabilizing the loop. We should not violate the phase margin in the, so ultimately stability issue will come only in the feedback. Open loop, there is no stability issue. But we check the phase margin in the open loop condition before connecting and make sure that when we connect, after connecting, the phase margin will not be violated or loop will not oscillate. So before connecting, we have first verified that yes, we are meeting sufficient phase margin, and after closing the loop, we will not have oscillation. So definitely, whatever capacitance we have put, it is for ensuring stable operation in the closed loop. Now now you can basically look at the closed loop bandwidth. You can see closed loop bandwidth 0 dB because ultimately it is unity gain, and it is coming almost around how much 100 megahertz, beyond 100 megahertz. So it should be 100 times whatever is the open loop because our gain is close to 100. So it should be almost 100 times the open loop bandwidth. So it is coming around 600 megahertz. What was the open loop bandwidth? Do you remember? Open loop bandwidth was how much? Do you remember?
So before connect, this was the old
Yeah.
133 hertz.
Yeah, 33 to almost 200 times it has increased. So assuming that, yeah, means approximately this is the order. So almost in the order of 100 increase you are getting in the bandwidth. It will not be exact because when you connect the closed loop, some of the DC bias conditions also change, and it will not be exactly same as the open loop behavior. But you are getting close to that much. In terms of orders, if you see, you had a gain of the order of around 100, and open loop bandwidth around 33 megahertz. Closed loop bandwidth is coming 660 megahertz, which is reasonable, which is close to our of the order of 100 times open loop bandwidth, which is okay as per expectation. So this is clear to all of you?
So like here do I measure the bandwidth also the 3 dB point because there is some peaking happening here.
The peaking is happening because of some inductive effect coming at the second stage, but that is not a problem. You can still measure the bandwidth at the 3 dB point.
So is it because like the gain is like positive and slightly less than 1, so that 1 minus 1 by A factor is coming negative?
This no, so this peaking etc. may be related to CGD of the MOSFET at the second stage. So those things can be with proper compensation, it can be mitigated. So zeros come, right? So we had discussed that the zeros can also cause this kind of peaking, and in the response, if the zeros are coming, we need to compensate the loop. So here, if you increase the capacitance like 0.3 picofarad, if you make it slightly larger, maybe the bandwidth will reduce, but that zero effect will also go, and it will become flatter. So right now, I think our bandwidth, if you look at the overall phase margin, it is also reduced to 35 degree, 35 degree. So if you increase the capacitance, that will become flatter, because zero will be further, the more is the dominant pole lower, the less will be the effect of all these zeros in the response. So in the phase response also, you can see what kind of response you're getting. First, from 0 degree, it is going all the way to minus 6, minus 45, minus 60, almost minus 60, and then again it is going down. So definitely we have effect of two poles coming closer because it is going all the way to minus 180 directly from 0, and then we have another jump towards the minus 360 degree at lower frequency. So you can just increase the capacitance, that will improve, so that will go down. Only thing is bandwidth will also reduce.
Like phase plot, I think here, right? So like one is around this around 550, and then the other is around 2 gigahertz. Okay. Yes, it's flatter now.
Okay, but so fine. So we can see overall the effect, and whatever you have been asked to do, we have done it over here. We have first of all calculated the gain margin, phase margin for the given condition. We have looked at the error also. Then we try to increase the gain. We increase the gain. Of course, we have not been able to increase the gain by a factor of 10. If you want to do it, you can do that. Right now, the target given to you was that you reduce the error by a factor of 10. For that, we will have to push the design a little bit more, and let us try to do that. Let us see whether exercise is same. Ultimately, the direction is same. If you want to do that, then again similar directions. You have to increase the input bias current, increase the W by L of the input device so that the GM goes up. Output side, you have to increase the length. That's all. So that will result in further reduction of bandwidth that we have to accept. Let us do that so that satisfy the problem requirement. So maybe you can make the current slightly larger in the first stage. Not this much, just at least 0.3, or make it 0.3. Yeah. W by L of the input device is already large, but in order to increase again, we may have to keep it. So make it 55 or make it 60. That is because otherwise the gain 60. Now you go ahead and increase the output impedance further by increasing the channel length. Maybe you can make it 1.5 micro, or you can even make it 2 micro. Make it 2 micro. The L you can make all of them all of the L you can make 2 micro. So overall, if you see, we have increased the length 1.3 times. W also in the first stage we have increased almost 1.5 times. Current we have increased. Overall, we have to see what is the increase factor. Accordingly, we will get some increase in the gain. The DC points we will have to take care.
Should I increase the width also by the same factor?
Width is okay. Width will mean the current will reduce. That is okay. So overall current magnitude will reduce. So only thing is if you reduce the current, the overall small signal current, if it is getting reduced, that will also affect the gain. So if you for that matter, you can basically reduce the L, increase the L of the first stage also. So if you increase the L of the load device M3 M4, if you increase the L also, that will make sure that the current in the second stage is not reducing that much, or the small signal current is not reducing. Small signal current, if you reduce too much, that will also affect the gain, because ultimately we are routing the current. So if the mirroring ratio is smaller, the small signal current will reduce in the second stage. So that we don't want to do. The small signal current ratio should remain similar, but at the same time, the channel length we want to increase. So remember that whatever current is mirroring from M3 to M6, the same small signal current is coming at M9. So if you don't, if you make the M6 much weaker than M3, the small signal current coming in M6 will reduce, and as a result, the small signal current finally coming to M9 through that loop will also reduce, and that means your overall gain will also drop. So in order to do that, in order to make sure that that does not happen, one option is that as you make the M6 and M8 weaker, that means you're increasing the L. You also increase the L of basically the load devices of first stage M3 M4, or you increase the W of M6 and M8. So both these options are there.
Okay, like so because I want to keep ratio similar. So which one do I do? Like I increase width of M6, M8.
What is
or-
M6 M8? What is the M3 M? What is M3 and M4 L right now? Yeah, so we
180.
can make it larger. So just you can make it maybe 0.5, whatever is the ratio of increase. You can maybe. So the ratio we should track, make sure that whatever, because ultimately we have assumed that whatever is the small signal current GM VGS produced by the first stage input devices, the same small signal current is routed through the second stage. But if you M3 M6 mirror ratio is smaller, M6 is W by L, M6 is much smaller than, or smaller than M3, then that small signal current going through M6 will also reduce. So that we have to see. So we have the other mirroring point is between M7 and M9. So that is also mirroring point. So again, the ratio of M7 M9 also, if your M9 is much smaller than M7, again the small signal current in M9 will reduce. Therefore, the current will also, the overall gain will also reduce. So let us see whether here, of course, if you have to do the open loop analysis again, it will be taking time. Let us see the closed loop after doing this DC analysis and the closed loop. Just like look at the DC. No, so this is not proper because the transistors are entering into triode region, and that is because of the uh, channel length of M3 and M4. You keep it slightly lower. Right now you have 0.5, so that ratio you have to keep M6, M3, whatever was the initial ratio, that ratio you have to keep. So make it 0.25 for the time being. Just make it 0.2 or 0.3, 0.3. You can increase the W also for the two devices, load devices, because this voltage has gone down, right? So if you can see, the overall gain has also gone up. If you see, the error has reduced to only 2 millivolt or 1.5 millivolt actually, but still the DC points are not very good. So we need to increase the W by all of this. So maybe, yeah, you can keep it 10. Yeah. Okay, so
Just too low, right? Because like VSG is too high.
no, that is okay. VSG is for the, because the W by L is also low, right? So we have increased the L also significantly. So that will be the case. That is okay. So now you can see that the overall error is 2 millivolt. Earlier it was 15 millivolt. Now it is 2 millivolt. So pursuing the similar strategy, we can go ahead. So I think this is about your second exercise that we had. And remember mirroring ratio. So when you are changing right now, the mirroring ratio has been slightly messed up. So whatever was the initial mirroring ratio, we should try to maintain. So earlier we had. So all we have to remember in this topology is that whatever is the small signal current in M3 and M4, the same small signal current will be mirrored to M8 and M6. So we should not try to reduce the small signal current. So for that ratio, we should maintain. And while doing that, the L of the output stages can be increased so that the output impedance, which depends upon L, is also increased. So that condition we should make sure. So that will ensure that you are not losing the small signal current. Whatever small signal current is produced by the first stage, you are maintaining that till the output stage. So I
Right.
hope all of.
In this one, so the ratio is around like 30. So if I make this instead of 40, if I make it 60 micro, then the ratio will be maintained.
That is okay. So you can do that. So in that case, the small signal current will be remaining same, and you are not losing the small signal current. You can increase. In fact, if you increase the W, then the small signal current factor will also increase. But at least you should not lose. Otherwise, there is no advantage of having large device at the input, because that is providing you good GM, and then GM VGS is the small signal current. And then if you are not scaling, if you're not sizing the next stage properly, you are losing some of that current. So advantage of having good GM at the input will be lost. Nothing changed much. So although I think the DC voltage has gone up. I think nothing changed. So did you check and save? I don't know.
Yes, I
Other side
made
also
the-
you have changed?
Yes, sir.
T2 and this one is just go to M9. Click on M9. T2. Okay. And the output stage is fine. Okay, so if you want to increase the gain at the second stage, one option is that okay, you can so the mirroring ratio can be increased to increase the current, and then L can be increased to increase the gain. There are the two options we have. I hope you understand the philosophy in this particular Opamp topology. And here we can see that as compared to 13-14 millivolt, we are down to 2 millivolt error, which is okay. So fine. So I hope by through this discussion, most of you can complete whatever assignment we had. We have already gone through most of it. The R value, as I said, it does create a high pass response towards the lower frequency, and it does interfere with your closed loop response to some extent. But again, that is just for the sake of DC biasing artificially the open loop. So we have removed it and we have done it without that. That is also okay. This strategy is also okay. Some people also put inductor, so you put big inductor in the feedback rather than R. What will happen? Inductor omega L is the impedance, and therefore at omega equal to 0, impedance is 0. It will be shorting. So DC point of view, it will be whatever is the output voltage, same will be the input voltage. But if you talk about say, the frequency, high frequency response, mid values response, there the omega L impedance will be much higher. It will be open circuit, so you can ignore it. So if you put a very large L, that is also valid. So some people do that also. But again, you may find some artifacts because of the artificially introduced L that we have to be careful about. So fine, I think this part is done. Any question from any of you on this particular part? I hope we have anyway done this. So by all of you should not take much time in completing this. Any question on this topology? You have to understand the circuit behavior. What is the strategy for increasing the current? Sorry, increasing the gain. Understanding how the gain is coming. The gain is coming because of the GM of the first stage and RO of the last, the second stage of M8, M9. And then the small signal current produced by M1, M2 is going through the load of M3, M4. And then from there it is mirrored. M3 current is mirrored to M6. The small signal current of M4 is mirrored to M8. And M6 current goes to M7. M7 current is mirrored again in M9. So this mirroring path, we should understand that, okay, how the small signal current is flowing. So whatever small signal current comes at the output stage, that multiplied by RO will give us the gain. Therefore, that is how we are trying to increase the gain. Increase the small signal current, making sure that GM VGS, GM1 VGS, whatever current is produced by the first stage is reaching to the output stage, and increasing the RO of the output stage by increasing the channel length. That's all. In this case, if we had a current mirror load or a current source load at the first stage, the story would be different. There, we would not talk about just basically routing the current, because there we would have good gain at the first stage itself. Okay, so let us look at our next topic. Any question before we conclude this?
Sir?
Yes.
Sir, in general, what will be the maximum value of W or L that we can go up to?
That depends on application, right? So many, in certain designs, like when you are designing a LDO, LDO means low dropout regulator. In a low dropout regulator, you need a MOSFET to supply current to all the other circuits. There, the W by L requires maybe even 1000 micro. That means 1 milli. So that is because it is required to supply that much current. Likewise, in certain low noise amplifiers, the front-end amplifiers where you are forced to keep the area large to minimize the effect of noise, increase the W times L area of the device. We have studied this in the noise analysis, right? So if you have to reduce the thermal noise, you have to increase the GM of the input device. If you have to reduce the flicker noise, you have to increase the W into L of the input device. So that will also impose its own constraints. So in those cases, you may have to keep several hundreds of micro also. That is possible. So it depends upon the requirement. What is the requirement? Even for advanced technology nodes, this is 180 nanometer. But even for advanced technology nodes, uh, 65 nanometer, 22 nanometer, we may have to. Right now, we are working on designs in, let's say, 65 nanometer. These are, some of the companies which are working with us on these designs. There are, drivers which are like common drain kind of buffers which are driving output load. There we need large devices. There also we having total widths of maybe, if you look at the driver device size that we have currently, it is almost 36 micro, 36, and that into almost 30. So it is almost 900 micro. So it is like a programmable strength. So that MOSFET size is programmable, but maximum size allowed there, that we have in the design, is almost 900 micrometer. So that is in 65 nanometer technology. So you can understand, wherever there is a requirement, we will have to keep the device size for special needs. That's why we say the analog side, whenever you're dealing with analog signals, although the technology may be very scaled, but still we have to use big devices to ensure proper operation, to ensure signal integrity, to ensure the right kind of signal behavior, and so on. Is that clear? Any question?
No, sir. Thank you.
Okay, so let us see what other things do we want to discuss. Where is my open? What was that? Open something. Let me share the screen and open that software. What was that? Let me share the screen. Sometimes, we feel that this parameter that we have to enter, or at least we have to see, there should be just, hover the mouse over the device and you should be able to see the parameter rather than clicking and opening. In Cadence also, we have still the same thing. So it would have been much more comfortable if we were able to just see the parameters by hovering the mouse. Now you are able to see the screen. Yes, can you confirm you are able to see the screen?
No, sir.
Yes, hello?
No,
No, sir.
sir.
We can't.
Yes or no? I'm not hearing clearly.
No, sir. We can't see.
No. I have shared my screen. Why it's not coming on sharing screen? Okay, desktop and then this. Okay, I missed some steps here. All right. So now you will be able to see the screen. Is that okay? Now documents. And yesterday, what did we discuss? Yesterday we discussed this thing. So these are the question. Anyway, question I have given you. Before that, the theory class we didn't have yesterday. Before that, we had discussed this. Why it is not opening? We had discussed. So you have gone through this common mode feedback, the fully differential circuit that I asked you to go through. Any doubt in that part? Fully differential amplifier. On clicking, why it is not opening? This is strange. It's open, right? God knows. Yes. Any question on what is going on? I'm clicking on the page is not opening. Let me use the mouse. Okay, the mouse works, but the pen doesn't work. Anyway, so yeah, so before that class we had discussed, of course, the current mirror amplifier, and we looked at the gain, etc. So this part I hope was clear, and I asked you to go through some of the lectures on the fully differential amplifier, starting from resistive load, and then I think current source load, and you might have seen the concept of common mode feedback using resistive divider and also using differential pair, basically. So all that is clear. At least the concept of common mode feedback for fully differential amplifier is clear to all of you. Any
Sir,
questions?
sir, I have a doubt in the experiment one. Like, if I connect 0.9 volts to the M1 MOS, we did for right now we did for 891 millivolts. But if I do it for 0.9 volts, I'm getting two pole graph. The graph shows it as two poles. I don't know where the two poles are occurring in the circuit you give
No,
for
you have
this
to
one.
first of all make sure that whatever voltage you're applying for that, all the transistors are in saturation. So if you change the DC operating point and have you made sure that your DC operating points are clear and the gain is DC gain is low
Yes, sir,
frequency
it's
gain is proper.
already,
What?
and the gain is at 30 dB. Yes, sir. And the
I'm not
gain
able
is
to
at
hear
30.
half the thing.
Can you hear me now, sir?
Yes.
Yes, so the gain is at 30 dB, but the graph is showing it as two poles. The change of slope is at 2 points.
So that is
I
fine.
didn't quite.
So here also we had two poles, but the poles were initially close together. But when we made one of them dominant, then it shifted towards low frequencies. If you use that is the purpose of using capacitor, right? So compensation capacitor at the output node is supposed to shift one of the pole towards low frequency so that it becomes dominant.
Okay, sir. Got
In
it.
this plot also we saw that the poles were, at least in the phase plot, we were seeing that the jump was directly from 0 degree all the way it was going to 180 degree in one go. That means the poles were close together, and the slope also after the 3 dB point, the slope was higher than 20 dB per decade. That also means the second pole is closed. So in order to make sure that the system is stable after closing the loop, that's why we put a capacitor and push the first pole towards low frequency. That will happen.
Okay, sir. Got it. Thank
That
you.
is the purpose of putting that capacitor at the output, right? The purpose is to push the first pole and towards low frequency so that you have enough gap between the first and the second.
Yes,
Yes.
sir. Without capacitor, the poles are significant, but with the capacitor, the poles are very near to each other in the graph.
With the capacitor, the dominant pole should be down towards lower frequency and the second pole should be at higher frequency. So you should get good separation between the two poles. That is the purpose. Are you getting
Okay.
that?
Yes, sir. Got it. Yes.
So you said something opposite. Whatever you are saying is opposite, that okay, without the cap you are getting good poles, and after the cap you are getting the two poles very close. That is opposite of what is expected.
Yes, sir. That was my mistake. I was actually seeing the graph from the other side.
Okay. So another thing that we should note is the biasing. So earlier, remember that whatever cascode amplifier we have studied, we have not looked into the biasing, like how do you bias some of those voltages. So let us look at that, cascode amplifier once again, and some other related topologies also, like folded cascode that we had discussed earlier. We will apply some of these Opamp to do something interesting. Maybe we will look into our some applications like voltage regulation, etc. Let us dive into that. But before that, let us look at the biasing options. So we will go for some simple biasing options. So remember our previous design where we had put a cascode load at the output, right? So we had the at this stage we had basically put PMOS and an NMOS stack to get the cascode. Now the question may be that okay, how are we going to realize the gate voltages of these two? And for that, again, we need to carefully choose the DC bias points of these. We know in terms of swing how it is going to affect, right? So this is a high impedance node. This is the point at which we are going to get dominant pole. and other nodes are. This one is also relatively high impedance, but as compared to this, still it is lower. So this is the dominant pole, and this is the stage which is providing us gain of the order of GMRO square. Now here, in order to look at the, first of all, we can look at the DC bias. That suppose you are using a current mirror over here, right? Whatever current mirror, simple current mirror, you are using a current mirror over here to establish the DC bias point for the M5. Let us call it M1, M2, M3, M4, and then M5, M6. I am still open to questions on the fully differential topology with the common mode feedback. So we can discuss the whole thing, but since I have given you the lecture, I hope we don't need to discuss the entire thing in detail. But still, if you don't have any point clear, we can discuss. Those things are also important because in many cases we need to deal with fully differential circuit. There also you should be aware of it. So in future also we will take some example, especially switch capacitor circuits, etc., where we need to operate in fully differential mode. So fully differential amplifiers are also important. We will again touch base on that quickly, whatever we have discussed in that lecture. Okay, so in this case, so what is the bias strategy that we can have? So here, if you're having in the DC condition, whatever I bias you are having based on the current mirror, you are having IB by 2, IB by 2, and the same IB by 2 over here, right? Same IB by 2. If the mirroring are same, the 3 and 5 mirroring ratio is 1:1, then you get same IB by 2 here also, and output stage also. So all we need is, yes,
so we
hello?
have two transistors named 5, right? Like,
okay, so make it 5A, whatever. So now, in order to bias this, one of the thing is that we can create a so let us look at the NMOS bias. So for the NMOS bias, we have seen one of the ways in this particular example is to basically have a bias current which is going to give us IB by 2. Let me, I will have to draw it a little bit advanced. So here. So we can size it such that the current here is also IB by 2. And then I need to have an NMOS stage where I can basically just have a diode connected connection, and on the top of that we can also have PMOS with another diode connected connection, and following that maybe we can also have another PMOS with a diode connected. So remember that where I'm not drawing the dot, there is no connection. So these are all, So here, what will be the situation? In this case, you are going to get the two PMOS over here. Now, if they are matched, like suppose I call this 10A, I call this 9A, I call this 8A, and I call this 7A. So these are all matched. So 8, 7, 8, 9, 10, all these are matched. So this circuit is just providing us the required VG for the 8, because here whatever current is required IB by 2, that is routed in 7A, and it will produce the required VGS for 7A. And here also for the M8 transistor also the same current is flowing, therefore it will again create the VGS for the M8 as well. And therefore you can see overall we can directly basically connect this one to this node, and also we can in fact connect the same node to the gate of M9. That way we get a DC bias point for our M9 as well as M8. So that is one way of biasing this Cascode stage. So if you are given any example that, okay, you simulate this particular topology, earlier I had not given you any technique for biasing. I just said that, okay, there is some fixed bias, but this is one possibility. All we need to do is appropriate VGS need to be created for the MOSFETs that are stacked. So here we are looking at these MOSFETs, and the same current is flowing in these two branches. We are establishing the VGS with the help of this bias branch. Whatever VGS is required to support that current in M8 and M9, we are creating similar VGS, similar gate voltages by pushing the same current in this bias branch, and then using those gate voltages for basically biasing the output device, output branch. That's all. And then your output is anyway being taken at this particular point. So that is all we have to do for appropriate bias point of the Cascode devices. There are other ways also in which you can probably improve the swing, right? So the allowed swing, etc., you can improve. That requires, say, whatever current mirror topology we have discussed earlier, right? Reduce swing Cascode. The same topology can be applied here as well. Like whatever I have drawn here, I can also do something like this. This is getting the bias voltage from the current mirror, IB, whatever VB is coming. This is VB. And then I can have a R over here, and then I can connect the drain voltage of this one, and then I can connect it to this one. So this is like our, whatever example we had discussed. One of the other option is that if you want to, so in this case, for example, if I push a current, whatever current you are having. So let us, in this case, one better option will be that if you want to have a reduced swing Cascode operation, one option is that you can generate this PMOS current, whatever PMOS current is required, you can basically generate it using a PMOS diode connected mirror like this. And now this same IB, whatever IB you are having here, suppose you are having IB by 2, same IB by 2 coming here, and this is going to mirror it in this one. And then with the help of that, these M7 and these two, 7B, call it 7B, 8B, 9B, 10B. So now the W by L of the 7, 8, 9, 10 pairs are same. 8A, 7A, sorry, 7B, 8B, 7, 8 and 8B, 7 and 7B, 9 and 9B, 10 and 10B. They are all remaining same. They are being supplied with the same current. And all I'm doing is I am applying the same reduced swing Cascode topology that we had discussed for the current mirror. That okay, given a input current source like IB by 2 for this particular branch, 9, this 8, 9 transistor, sorry, there is no 9 in this case. I'm only biasing, I'm only getting the bias for 8. So for, I have written 9 here. 9 for 9, I will have to do the same thing on the PMOS side. I have not drawn the 9. So let me do that also. For the 9 part also, I can insert another PMOS. So that will also look like similar. So just like we have the reduced Cascode, I can insert another resistor over here. And bias it in the same way, like this one. Let me draw it a little separate, otherwise it is also possible to use different branches for both of these. This is PMOS, PMOS, and just like we have done for the NMOS, here also we'll do the same reduced swing Cascode biasing. Sorry.
So like I didn't understand this part. Like, so could you explain this again? Like we are using that reference voltage VB, and then what is this for? Like, so this
This is for biasing the this is for biasing our Cascode devices, right? So that's what we are trying to do over here. So one option is, so let us, in order to make it slightly simpler, let us keep the bias of the PMOS and NMOS separate. So let us first look at the bias for the Cascode of NMOS. So the first, simple biasing scheme, this one it is clear, like whatever I drew here, like this part composed of this particular segment. Is this clear?
so here 10A, I didn't understand the function of it.
No, the 10A, it is just providing us a diode connected, the VSG required, right? So this is not being used. but just in order to make sure that the bias voltages are matched, right? So here, whatever VSG we are having for M10, the same VSG will appear for 10A, and corresponding to that, once again you will have an additional VSG for the 9A. So in this case, the bias voltages will be adjusted according to the W by L of 10A and 9A. If you don't put 10A, if you just directly connect it to VDD, what will happen? This voltage, the source of 9A, it will directly go to VDD. And therefore, what will be the gate voltage of 9A? VDD minus VSG, whatever is the VSG required. But that is not appropriate for 9 because there is also an additional VSG drop because of M10. So in order to accommodate that, we put the diode connected M10A also, so that we get a VSG matching with that of 10 in the 10A. And on the top of that, we get another VSG because of the 9A. Is that clear?
Okay, yes. And so the right one, like this porting resistors, like
Right
across.
one is our cascode, right? So we had discussed this reduced swing cascode mirror. Do you remember? Reduced swing cascode mirror, current mirror. Yes. The same thing. So what I have done is I have just, this is like a current source. This is just providing a particular current source to this branch, right? So this 8B and 7B, they are like the current mirrors which are getting this I ref, which is equal to IB by 2. So this branch, it is just taking this, if I call this, say, 7C, the 7C is just taking the voltage bias VB and generating the IB by 2 and routing it to the PMOS, and then the same IB by 2 comes here. So this is just providing the current. So again, the diode connected, I have to remove this one. So this is just providing the IB by 2 current to this mirror branch, right? So this is just like our mirror branch, cascode current mirror with reduced swing. This part is the mirroring branch. This is just helping us getting that IB by 2 from the top. That's all. Here the IB by 2 is at the bottom because here we can see that IB by 2 is coming from the top and we are basically mirroring it in the NMOS. But now here I need to supply this IB by 2 to these NMOS mirrors. And for that, I have routed it with the help of these PMOS transistor, this PMOS mirror, and it is coming IB by 2 here. And then with the help of that IB by 2, I am biasing these two transistors, this 8B and 7B. This 8B and 7B are like our cascode current mirror with reduced swing. And they will, here we can use this particular bias point for M8 directly. So this can be used for biasing M8. Likewise, we can also basically use another branch for biasing, say, M9. So this scheme will be advantageous because it will provide us higher swing at the output. If you remember the cascode current mirror with reduced swing, it helps us in getting higher swing at the output. This will also work. This will also provide us appropriate DC values required for the gate of M8 and M9. But the swings will be at the output. The swing available will be smaller because it is the simple cascode, because you are having VGS 2 VGS drop. Here also you are having VGS drop for M10, and here also you are having VGS drop for M9. Whereas in this case, remember, in the current mirror with our reduced swing, we are having the overall voltage that you can have out the output is only 2V over drive, right? So we can have the minimum output voltage as 2V over drive rather than 2VGS, or basically 2VT plus V over drive. So those things we have discussed earlier. If you bias an output branch like this with direct normal current mirror with devices like M10 and M9, which are diode connected, it will require 2 VGS drops. So here we are having VGS drop for M10, and on the top of that, another VGS drop for M9, right? So it is requiring 2 VGS drop, and then only the output DC comes. If you have current mirror based biasing where you are using reduced swing cascode, there the swing required is only 2V over drive, or basically the headroom required is only 2V over drive. So those things we have discussed earlier. you can use this simpler scheme and try to basically look at the DC voltages developed. What is the DC voltage being developed at the gate of M8 and M9? So DC voltage at the gate of M10 is anyway decided by the DC voltage at the first stage. So M10 does not need any biasing. M10 biasing is here, but M9 and M8 requires biasing, and for that we are using this particular branch. And the purpose of using these two direct connected transistors M8 and M10, M10A and M8A, is to get appropriate VGS drops. So like M7A, or this one is M7A carrying the same current as M7, that same current goes into M8, and therefore now this is direct connected. It will develop a VGS required for M8. Therefore, that VG can be applied to this 8, and therefore it will make sure that it is also having similar VGS, because M7 is anyway trying to enforce the same current. Now you are applying the same VG as M8 in this one. Therefore, it will also make sure that the gate voltage of these two M8 are same, and therefore your the VGS required and the VDS are also matching with the reference branch. This is the reference branch or the biasing branch. Likewise, for M9, once again, we need a certain VSG, and for doing that, we are first of all using a M10A. So this top device is M10A. We are direct connecting it, and since it is carrying the same current as M10, remember, because we have biased it with same IB by 2, it is carrying same current as M10. W by L is also same. Therefore, it is also getting a VSG, which is similar to M10, close to M10, and then we need to generate the gate voltage of M9. So the gate voltage of M9, again we are using 9A. So this 9A, again we have direct connected it. What will it do? It will again enforce that there is a VSG drop between this node and this node, right? So it will ensure a VSG drop between the source of 9A and the gate of 9A. So it will establish a required gate voltage for 9A so that it can support the same IB by 2, and then that gate voltage is appropriate for biasing the M9 of the output stage, because ultimately it's also supporting the same IB by 2, and it is also basically having similar source voltage as the reference branch. Is that clear? Yes. Is this getting clear? Why we have this is a reference branch, this is a bias branch, which is not contributing to the amplifier operation. This is just for generating appropriate bias for M9 and M8. That's all.
So M10 is it's like M10A is diode connected, and we have the same current like IB by 2. That's why we are saying it's properly biased, right?
Yes. Bias current is coming from M7. 7 is driven by the same VB. Therefore, it is going to ensure same bias current in this entire stack.
Yeah. Okay. Yes.
And 10A and 10 are matched. Therefore, you will have the same VGS, whatever VSG is required for the M10, the same will be available for 10A.
10 is the input device, right? That one does not have any biasing. It's only for like 9
It is
and
not
10.
an input device. It is just a bias branch. M10A is not playing any role in the input-output processing. It is just for biasing the other transistor. 10A is providing the VSG drop, and on the top of that VSG of 10A, you have the VSG of 9A. They're just direct connected, right? So you read the two VSG drop, one VSG for 10A, another VSG for 9A. So I need to generate the appropriate voltage for the M9, and for that I am using same transistors, same as 10 and 9 in this branch, and pushing the same current, so that I get the two values of VSG generated in the stack, and then I bias the gate of M9 with that. M10 does not need a bias because M10 is anyway connected to the output of the first stage, and that is taking care of the DC bias. I don't need to apply a bias there. But M9 is not having DC bias. For that, I am generating the required gate voltage with the help of this 4 transistor. Is that clear?
Yes, sir.
let us look at some other example, like it will become a bit more clear when we look at folded cascode. Let us look at folded cascode example also.
So instead of using this bias branch, can we just use the mirrors already in the circuit, like M3, that
That's what we are doing,
M5A
right? We are
current?
using a mirror only. So what are we doing? M7A is a mirror which is taking the current IB, and it is then how will you generate the gate current, gate voltage of M8 and M9? You need to create the same stack, right? So whatever is the stack.
Give the bias of M3 directly to M7 and we adjust the W by L. And for M9,
Wait a
we
minute.
give
M3.
bias,
Where is M3?
sorry,
M3 is here.
M5
How will you
is
give the bias?
bias of
M5
M3 and give to M9, right? So and adjust the W by L.
bias of M3 to
M9.
Oh, that is not
that-
appropriate, right? So you have to look at what is appropriate. So look at the VSG drops. So here in the output stage, M10 is biased with the gate voltage of M3. Whatever is the gate voltage of M3, it is biasing M10. So I would like to keep the gate voltage of M9 lower, right? So I will not like to have exactly same gate bias as M10. So I am trying to keep it lower. And for that, I am generating a VGS drop. So M10, whatever is the VGS G of M10, I am creating that same VSG with the help of 10A in this circle, right? This. And then I'm adding another transistor 9A, which is going to create another VSG for biasing the 9. We're getting the right gate voltage for the 9. Is that clear?
Yes, sir.
So you can calculate the swing also, whatever the swing output swing achievable in this case, because you know the gate voltage. So here, as compared to the gate voltage of 10, so we have VSG of M10, and then you have the VSG of M9, right? So the two voltages are coming VSG 9 plus VSG 10. These two VSGs, so the gate voltage at the 9 or the gate of 9 in this case is what? VDD minus VSG of M10 and minus VSG of M9. And therefore, what is the output maximum possible? This plus mod VTP. So this is the VDD minus this is your actual DC point, and the maximum swing possible is this expression plus mod VTP. Likewise, on the lower side also, you have the VGS of M7, and you have basically the VGS of M8. So you are having, as compared to now the M7 over here, that will basically develop the VGS 7, and then you are creating the VGS of 8. So this point, of course, it will get as compared to the drain of as compared to the drain of M7, you are having VGS of 8 also, so plus VGS 8, assuming that you are having almost similar gate to the gate and drain voltages of this M7 are also remaining similar, because it is mirroring IB, and assuming that in the IB you have gate and drain voltage similar. Likewise, for M7 you will have similar gate and drain voltages, and then on the top of that you have another gate to source voltage of M8. So this is going to be VGS7 plus VGS8, and that is the gate voltage of M8. So this minus VT is the minimum allowed swing. So in this case, of course, this basically gives you the swing at the output, and you can see that is ultimately from plus VT to minus VT. That is what you are getting. So if the swing in this case, you can see it is going to be if VT is 0.4, so 0.4 plus to point, output DC voltage plus minus 0.4. That's what you are going to get. So because you have a VSG7 plus VSG8, and here you have VSG9 plus VSG10, they are going to be similar in magnitude. VDD minus this VSG and 0 plus these two VSG similar in magnitude, and this is plus VT and this is minus VT. So on the top of that, you will get therefore the output DC point plus minus VT almost, you will get the swing. Let us look at a fully cascode mirror. That will become more clear. That is also having similar biasing, almost exactly the same biasing at the output stage and with cascode. The first stage is anyway simple. So in the earlier classes, we have discussed the cascode amplifier for the single-ended version. Now, if you look at this particular topology where you have folded cascode in the differential mode, this can also be done in two ways, either fully differential or it can be single-ended output. So folded cascode, if you see exactly the same biasing strategy. And this is also popular topology, and it has an advantage that it is relatively lower power. At the same time, it also has very high gain and dominant pole. So the circuit, the concept is similar to what we have discussed earlier. Here, this is the cascode branch, just like what we drew a few minutes back. 2 NMOS, 2 PMOS in stack. We will have some bias VB. We will draw that and we'll see how to do that. VBN1, VBN2, sorry. And then this is also requiring a bias, VP, whatever, VB. VB means bias, VBP, whatever, VBP. Call it VBP2 and then call this VBP1. And now you have basically the input side, the input differential pair consisted of NMOS transistor and the current source. Now, in this case, one of the simplest biasing strategy, if you want to have a single-ended output, if you want to have a single-ended output, in that case, you can basically have a current mirror kind of topology, just like this. So you will, in that case, you will require only biasing for this particular node and this node. The lower two are basically acting like a mirror. Or you can have fully differential version also. In that case, you will need the biasing for all of these four, just like I had done right now. You will in that case you will need the biasing for all those four. Let us first look at the simpler version where you have the two nodes below. They are basically diode connected. That basically means that the small signal current, whatever enters into this branch, lower branch, it will be mirrored into the output branch. That's all. And the output node will be this. This is a single-ended output. Just like in case of your differential amplifier with current mirror load, here also what we have simply done is the cascode branch, we have done the mirror connection. So it is basically, if you look at what is happening, so this is the input pair M1, M2. Let us look at the signal. What is the signal doing? How it is behaving? Call it 5, 6, call it 7, 8, 9, 10, 11, 12. This is a popular topology which comes very frequently. If you read papers, etc., you will find this thing being used everywhere. So it's important that you are aware of this also. So here, if you look at this, suppose VBP1, VBP2 has been decided by appropriate biasing for the time being. First, need to understand the biasing, the circuit behavior. What is the circuit doing? So if you have, say, first of all, bias current point of view, whatever bias current comes from this M5, M6, suppose this is IB, both of them are biased and they are providing some bias current IB. So you can see that ultimately the same bias current is getting divided into two branches. One is going into this direction, another is into this direction. So you are having the net bias current of M1, M2 coming through I3. So you can call it whatever. You can call it, say, IA. Now this IA, therefore, is definitely it is less than IB, because IA plus whatever is going in this branch, you can call it, say, IC. So in this case, IC plus IA by 2 equal to IB. I can write that, right? So whatever is IB coming from M5, that is supporting the current in M1, which is IA by 2, and it is also supporting the current in M11, which is basically, I have written IC. Therefore, IC plus IA by 2 equal to IB. This is a DC bias requirement. So when you are sizing this transistor or mirroring current is being established, this is the ratio we need to be aware of. This is the current division taking place. So the top source constituted of M5 and M6, it is providing current, it is like a current source. It is providing current to both these branches, and M3, of course, it is determining how much current will be consumed by the input branch. So it is taking some fraction of IB. So IB has to be larger, significantly larger, maybe double or at least 1.5 times that of IA. That is clear. Now, if you look at the input pair, input is just like a differential pair. Only thing is, at the output side, you have some load connected, right? So otherwise, this is our good old differential pair. And if you look at the AC behavior, if you look at the small signal AC behavior, again, I can say that this point is going to be AC ground. So I can comfortably put an AC ground at this particular node between M1 and M2 source. And then what does it become? So it becomes very similar to our earlier example. So if you look at the half circuit, resulting half circuit, so if you have a signal, differential signal coming at the gate of M1 and M2, this is AC ground. What is happening? GM, suppose this is VD by 2 minus VD by 2. So this is going to produce GM VD by 2 current in M1, right? Small signal, and the opposite side will be minus. Now, this current is constant. Assume that this is RO is large and this is acting like a good current source. So this M6 and M7, sorry, this M5, M6 are acting like good current source. Suppose they are not taking away any current, their RO is very large. And therefore, this small signal current, for the time being, we assume that this entire current will be flowing into this for the time being, because you can for the time being also you can replace these two. So suppose the actual ideal behavior is that we need a current source at the top. So to simplify things, suppose for the time being we have a ideal current source at the top. These two are ideal current source. So then it becomes easier to see. So this GMVD by 2, in that case, this is ideal current source, I bias, whatever, IB. So that doesn't take any current, any small signal current, it will remain constant. Therefore, this GMVD by 2 will be going into this branch, right? Whatever GMVD by 2, it will be going into this branch. And likewise, minus GMVD by 2, VD by 2 will be coming into this branch. Is this clear? This is the current folding happening, just like in our single cascode, folded cascode amplifier. Here also, the small signal current produced by M1 and M2 are getting folded into the other branch, M7 and M8. Is this clear? Is this becoming clear? Like what is happening to the small signal current generated by M1 and M2? Yes, hello? Anything, any, is this clear?
Yes, sir.
I don't know for how many people it is clear.
So not like completely clear, but I can compare it to the single stage.
Okay, so let us this also let us for the time being keep the simpler version, fully differential. So fully differential, what is the scenario? These are now the half circuit is even simpler. Half circuit for fully differential case, what is it? This is the cascode stage. All of us can see the second stage. This is the cascode stage, and the first is the input differential pair. This is the AC ground. Now it is fully differential. So what is the half circuit of this particular configuration? Half circuit is simple, right? So you just have the input pair M1, it is AC ground, and on the other side you have IB, and you have the cascode. This PMOS gate is AC ground, and then you have two NMOSs. Gates are AC ground. Output is here. Is this okay? This is your whatever 11, 9, 7, etc. So is there any problem in this? So here what is happening, whatever small signal, if you are having VD by 2, so GM VD by 2, whatever small signal current is produced, if this is a good current source doesn't change, the entire small signal current flows through this. And that's how we figured out what is the gain of this cascode stage, right? So this folded cascode we studied earlier, single and one, this thing we have exactly this thing we have studied earlier. We just figure out what is the small signal current going into this. This is like a common gate stage, right? So whatever current GMVD by 2 is provided here, it is going into this one. It is passing the same current into the load, and therefore here whatever is the load, ultimately this is like a common gate stage. You are having some input current coming, which is equal to GMVD by 2, and you have some load connected over here. What is this load? Looking downward, it is of the order of GM RO square from this drain. This is the scenario, and this is the output V out. So therefore, if this is the this is common gate stage, M7 is like a common gate stage where the input current is GMVD by 2 at the source of it, and therefore the gain is simply going to be GM output voltage is GMVD by 2 into GM RO square, and therefore we get GM RO whole square. That is the story we had discussed earlier. Do you remember?
Yes, sir.
So I don't know. I think a lot of people are not recalling what we have discussed. So if we have discussed Cascode, the thing is, if we don't give simulation examples on these things, you forget. That's why I should have given simulation examples on every small thing. So so what is not clear in this? So this small signal in detail we have discussed. The small signal model for this simple cascode also and folded cascode also. This is same as what we have discussed earlier. Nothing new. So we have just looked at the half circuit analysis of this differential pair. Other half is also going to behave like this, and therefore we can just take the difference between the two outputs, and our output will be given by GMRO whole square into VD. That's all. So is this clear? What is the is there any doubt in this small signal operation?
So like M5 and M6 we replaced with ideal current sources. If we keep them, it will be.
If you keep them, then the current division comes into picture, right? So we have discussed this earlier also, that if you have actual real current source, if you have say this M5, right, whatever I had called it, suppose this was M5. So what will happen? This GMVD by 2, now it will have current division, because earlier if it is the ideal current source, it would not take any current, a small signal current, but now there is a current division. So you have to look into R up, R down. R up is RO. What is R down? Looking into the source of M7, what is R down? Oh. These things you have to remember. If you don't remember these things, there is no hope in analog.
Approximately so like GMRO into GMRO whole square, I think, right? Because at the lower one we have GMRO square.
This is impedance looking in the source of a MOSFET where the drain impedance is R. So if you have a drain resistance RD and gate is AC ground, looking into the source, what is the impedance? That is RD upon GMRO. What is RD? GMRO square. What is in this case GMRO? So it is GMRO only, and therefore you are left with RO. So looking down also you have RO, up also you have RO, therefore you get by 2 factor. Is that clear?
Yes, sir.
And then in fact we also need to look into another RO, which is because of this guy. If you want to have exact analysis, you have 3 ROs: RO of the M5, RO of the input device, and RO of this stack. The impedance of this stack is also RO, and you have the RO of the M5 and RO of M1 itself. So this GMVD by 2 gets divided by 3. The 1/3 goes into the branch constituted by 7, 8, and 11. Is that clear? So that 1/3 factor will come. Is that clear? Earlier we were ignoring it, if you had an idle current source, you can, and here also the RO of the input device is large, you can ignore. But now if you if you're considering real ROs or finite ROs, then you need to take into account the division between these three ROs at this point, because the M5 is also providing RO, M1 is also providing RO, and the impedance looking into the source of M7, that means the stack of M7, M8, sorry, M7, M9, and M11, they are also having impedance equal to RO. Therefore, there are three ROs. So 1/3 of that current, GMVD by 2, actually go into the stack of M7, M9, and M11. Is that clear? In the earlier case, if you had discussed only the normal cascode, what we were discussing, normal cascode, if you don't have folding, then this was the scenario. This is the input V in, this is some bias voltage VB1, VB2, VB3, somehow they are generated, forget about it how they are generated, and then we said that okay, output voltage is this node, and then here on how did we get this gain? So this is producing GM V in, whatever is the GM1 V in is a small signal current, and here also we said that looking upward, the impedance is RO. Looking in the source of say M2, M3, M4, looking into the source of M3, the impedance is RO from the same logic. And then this is also having RO. Therefore, we get only GM V in by 2 going up. And this device, whatever current enters into the source, the same exits into the drain. And therefore, now in the impedance in the drain is GMRO square. And therefore, this small signal current gets multiplied by this, and we get the output signal, which is GM square RO square by 2 into V in. Right now, what is happening in the folded cascode case, the only difference is that you have another current source, M5, that is having its own RO. So now 1/3 of that GMVD by 2 will actually go into M7. Is that clear?
Yes, sir.
So from that logic, I hope you can understand that this particular differential amplifier, if we take the output fully differential, in this case it is fully differential because output over here is fully differential. It is going to give us this GMRO square by 3 gain. Any problem in this? GMRO whole square by 3. So this part we understand. Only thing is right now we don't know how to bias these gate voltages. So we have three bias voltages to be obtained: VB N1, VB N2, and VOP VBP2. These gate voltages, and then of course you have the upper one also. I have currently made them current sources, but ultimately they are also transistors. So here also ultimately we have two transistors in reality. So their gate voltage also we need to get.
So here also
So
we can use tower, right? Like that parallel branch of just biasing.
yes, so that is one thing, but we also need to look at have you studied the lecture, like whatever video lecture I gave you on common, because this is fully differential, and what I wanted to first discuss is the single-ended one where the output is single-ended. Now, from before I study the bias of this one, I will first complete the discussion on the folded cascode op-amp with single-ended output. How will that look like? So for a single-ended output, what I need to do is I need to, right now what is happening in this in the fully differential mode, in the stack, both the branches are getting similar small signal current. Whatever small signal current is provided by the input branch, it is getting driven into or folded into the two vertical branches by similar amount. Whatever is the small signal current produced by M1, M2, it goes into these two vertical branches. There is no doubt in that. This is coming from our analysis. This is clear. Now, that was just like when we had this fully differential amplifier with active load, right? So if you remember this thing, if you have what is happening in the fully differential amplifier with active load, if this is the current source load, this is some bias VB, and then you have the input devices. This is simple differential amplifier with active current source load, right? Here, this bias, output DC bias is not set properly, and we need to apply all kinds of feedback, common mode feedback, etc., that we have studied in that video lecture. I hope you have studied. I'm not sure if you have not studied, then please go through that. We will discuss that briefly, but not in so much detail as in that lecture. So these concepts, these are whatever we are studying right now. These are tools. Once you have those tools in your hands, then you can do all your, whatever projects, whatever design, whatever engineering you want to do, you can do. If you don't have the tools, you can't do anything. So these are whatever concepts we are studying right now. These are all tools. Once you know the tools, you can do, you can break the mountain, you can do whatever, you can, do a lot of interesting stuff. But before you do anything, you need to know the tools. So that's why, some of these fundamental important things, which are frequently used, which are, we are used to it. We frequently use it in many circuits. So that's why we should be aware of this. That's why we are studying all this. So here, in this case, in this particular amplifier, we have, suppose output DC point is taken care of, you have biased it somehow using common mode feedback. In this case, whatever small signal current is produced, suppose is VD minus VD, differential signal, this is AC ground. So GM VD, or call it VD by 2, whatever, GM VD by 2 minus GM VD by 2. So the current goes, the same small signal current goes into the PMOS, and then we get an output over here. However, when we connect the current mirror load, what we are doing, that also we have discussed. Sorry for the bad drawing. Current mirror, what is happening? Here, whatever is produced, GM VD by 2, the same is mirrored in the output. The output side, this is the output branch in this case, single-ended, and the same is mirrored here, and minus GM VD by 2 minus GM VD by 2 is coming from here. So taken together, if you say you reverse the sign, it becomes plus GM VD by 2, and then we have the net gain, GM VD by 2 plus GM VD by 2 into the RO. That's what we have seen. So in this case, it is a current routing. So this node, we are not getting enough swing. This is not going to give any gain. It is just basically mirroring. Whatever small signal current is produced by one branch, it is mirroring into the other branch. And at the output, we are summing up these two current and getting the output. Same philosophy is there for the folded cascode with single-ended output. So in this case, if I, let me copy this. So if I copy this, I think this go hide, and then copying was, I think, this one, right? So this one, if, no, what was the copy as this one? So if I take this whole thing to see, then I go down, I think I will be go down. I don't know how much space they will provide. So Control plus V didn't come. I don't know what is going on. So I copied this. Copy what? Copy is not happening. Left. This is horrible. I don't know what it is doing. Never paste the right place. It just overlapped it and killed it. What is this? Simple copy paste operation. Undo also it will not do. Where is undo? Undo also is not doing. See? Horrible tool. I mean, I don't know how do they develop the software. And it will not even give me the opportunity to correct or what. I'm correcting, but it is not correcting. Anyway, now it is all spoiled. This one is also spoiled. It didn't copy. Now it is letting me undo. Pathetic. Super pathetic. If I want to. I don't know. This is not moving also. So I don't know. Again, I have to draw the whole thing. This is completely. Not. I don't know. This is. So let me. What can be done? Anyway, this is spoiled. So I don't know. This is strange. Yesterday I had seen that it is copying properly, but it messed it up. I will draw this whole thing again. This is the pain. What is the time? Time is also passing quickly. So just have some patience. Let me finish this. Sometimes these tools are misbehaving. What can be done? So in order to convert this into single-ended, all we need to do is use a diode connected current mirror topology at the load side. Here we have the same PMOS biased with the help of some current mirror, and you are basically routing the signal to the input. And in this case, what is happening, if you see the small signal current which is coming in this branch, right? So whatever small signal current in this branch and it is coming into this branch, right? So this will get mirrored into the output branch, right? So this is the output in this case, a single-ended output. So now in this particular example, you can see the if it is your M1, M2, and you are getting say GM BD by 2 plus GM BD by 2, and as we have seen that 1/3 of that will go inside GM BD by 2. So this goes into this, and these two transistors, if I call this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if you look at the 7 and 9, they are effectively once again mirroring the small signal current into M8 and M9, right? So whatever small signal current flows into your M7 and M9, the same current comes at the M8 and M10, and then we have the small signal current which is corresponding to say VD by 2 GM minus, because this is you have minus VD by 2. So minus GM VD by 2, corresponding to that you get the 1/3 of that into M6. So this one is also getting minus GM VD by 2 into 1/3, right? So this current goes into M6 and appears at the output, whereas the same current magnitude appears from M8 and 10 at the output. So it is also behaving in a similar manner if you see, right? So the only thing is mirroring is happening through this cascode mirror. So if you look at M7, M8 and M9, M10, they are nothing else but our cascode current mirror. If you remember simple current mirror versus cascode current mirror, we have studied this, right? So in this case, M7, M8 and M9, M10, they are forming a cascode current mirror. So this mirroring operation is clear. Just like in the simple differential pair with current mirror load, we were getting the current, GM VD by 2 minus VD by 2 coming together at the output. Here also, we are, if you observe the current direction, the bottom two branches, M7, M9, they are just whatever small signal current they are receiving, they are mirroring it into M8 and M9. Sorry, M8 and M10. And M6 is anyway receiving its own small signal current from the other branch. So therefore, the small signal current coming from M6 and M8 arrive at the output, and whatever is the overall output impedance over here multiplied by that gives you the overall gain. So here, as compared to the previous case, we have at least some degree of self-biasing achieved for the lower branch. Lower branch, we don't need biasing voltages. These two voltages are, basically obtained by the diode connected transistor directly. Depending upon the bias current that you have established, they will generate the required bias voltages at these 2 points. However, for the upper two transistors, you need to create the appropriate bias point. This is clear. This operation is clear how it is behaving like a single-ended output and why it is behaving like a single-ended, differential to single-ended OTA. Is this operation clear? This I need to bias VBP or VBP1 and VBP2. This voltages I still need to generate. Is this clear quickly?
Yes, sir.
And now generating these voltages, again, we can make use of similar strategy, because we know that, okay, this is the W by L of M4 and the current. So ultimately for M4, we are going to take a current source because we need a certain bias current IB. So for that, we can use a current source. So you have some IREF, and from that IREF, you are biasing the M3, M4 to get an appropriate current at this point. So the VB of the gate voltage of M3, M4 simply coming from a current mirror in this particular scenario. The gate voltage of VB2 that we need to generate. So for that, once again, we can pass the same bias current. So one option is that you can pass the same bias current into a similar transistor, which is, say, same dimension as M4, and then you can have a diode connected transistor for, say, M6, and likewise two NMOS diode connected transistors at the bottom, which are also going to play similar role as M7 and M9. So you can call it 9A, 7A, and you are having same IREF over here. This is suppose you call it 4A, 4A, and this is you call it maybe 7, 9, right? So 5A. So let me call this also 3A so that it is consistent. So 3A and 5. Now what is happening? So you are pushing the same IREF over here, and then for the same IREF, whatever is the gate voltage of M9 and M7, the same voltage will produce here, same dimension, same current. The VGS is going to be same. So whatever is the gate voltage VG9, VG7, same thing will come here, VG9, VG7. No doubt. And then you have the same voltage VG3, because the same bias current, same size, again the same, therefore same VG3 is coming at the gate of and now if you look at the gate voltage of M5, so you have actually the same gate voltage coming at the same drain voltage coming at the gate of M5, and therefore in this case you are getting actually the gate voltage of M5 becoming, you know, same as the VG7, and because these are basically PMOS and NMOS, so there is no problem if you have the same voltage at the gate of these two, and it is basically generating the appropriate bias level with the required VSG drop for the transistor number 5. So this VSG drop will be appropriate for biasing the M5. So the use of all this tapped transistor is just to get the right amount of VSG drops with which we can get the gate voltages for biasing the actual transistors in the circuit. So with the help of these 9A, 7A, we obtain the same VSG, whatever VGS required, VGS 9, VGS 7, and then also we for the same VG for the 3. And then by putting a diode connected M5, we are also basically getting the VSG generated for M5 so that it can support the same current. Is that clear? So this is again a simpler scheme. We can go for our reduce the cascode swing, reduce cascode biasing for better swing conditions. In this case, once again, you can see what is the output voltage min required. That will be VGS9 plus VGS7, right? So you have one VGS drop for the M9, another VGS drop for the M7, and that is giving you the gate voltage of M7, and that is the same as gate voltage of M8. So minus VT8 is the V out min. So V out min is limited by this. So whatever is your VGS of 9, VGS of 7 minus VT8. And likewise on the upper side, it will be limited to whatever is the gate voltage, whatever is the bias voltage at the gate of M5, which is in this case generated by this particular mirror. So is this clear? This is how you can bias this kind of cascode stages. and you can also go for cascode, reduce cascode swing. We will, we have discussed it earlier. Probably for today we already getting late, but at least the simple biasing with the normal cascode mirror, that should be clear enough what is happening. And then probably I can give you some simulation exercise where you can try to connect these and see how the VGS are getting developed, and then in the output DC point over here, how the output DC is coming. Here also it is a high impedance node, and however, if you are having appropriate bias voltages generated for VB2, VGS7, VG9, in this is just like a differential amplifier with current mirror load. This is also going to be self-biased. You will you basically get a self-biased output node, and in this case, it is going to be dominant pole once again, because here you're getting the impedance of GMRO square. So the high impedance node, at the same time it is self-biased also because of this VG7, VG9 mirroring. Is that clear? Are you able to understand this, the stack, how it is working, how the current folding is happening, how the biasing is happening?
Yes, sir.
Okay, so we will. So there are many other interesting modifications for this one also that we can discuss maybe later, especially for the fully differential case. For the fully differential case, how do we bias it? It is again in line with whatever discussions we have had for the video lecture that I have given you. In the video lecture, I have described the biasing strategy for fully differential amplifier with active load. The same strategy will be applied for biasing the fully differential version, where the bias of VG7 and VG9 also need to be generated. And that is, in that case, we also need to make sure that the output DC point is properly biased. So for that, we again use common mode feedback. But in that case, it will be for this stack. In the case of differential amplifier that I have discussed in the video lecture, it is for a simple differential amplifier. But similar strategy with some modification can be used for biasing the fully differential cascode or folded cascode amplifier also. So if you have not yet completed that lecture, please go through that. Based on that, we will have a discussion tomorrow, so that both these things, fully differential topology, whatever fully differential topology you have, whether it is folded cascode, whether it is your current source load, whether it is a two-stage amplifier, fully differential, all those things, biasing become clear. Strategy is same. Once you understand the video lecture that I have given you, the same strategy will be able to understand how to apply it for biasing the fully differential version of this particular folded cascode amplifier. Is that clear?
Yes, sir.
Okay, so means I'm surprised that many of you, I'm not sure whether when I described this one, basically recall this one, the simple cascode, basically folded cascode that we had discussed earlier. It seems like many of you are not recalling, so that will be a problem. If you don't recall, then what is the point of studying? So whatever important points are being discussed, it is important that you remember. So some of these things you should keep in mind. So these are tools. If you don't have tools with you, how will you apply anything? How will you understand anything? If you have to read a paper, if you have to read a document, if you have to read a practical design, these things will come again and again at different places. So if you don't know those tools, you will not be able to understand any practical design. So therefore, many times we also encounter new circuits that we have probably not worked on earlier. So newer technologies, newer nodes, people have done different kinds of modifications. But if you understand the basic things, like fundamental things, like what happens if you cascode the transistors, what is the signal flow, how the signal is getting folded, how the mirroring is happening. If you understand these basic things, then understanding any op-amp will be easy. Even if you are given a complicated op-amp structure with many stages, you will be able to see what is happening in different stages, what stage is doing what, right? Previous stage also I discussed, the differential stage is not providing much gain. It is only providing GM, and the actual RO is coming only from the output stage. So that is, if you look at the amplifier structure, you can see that, okay, first stage the current mirroring is happening and how it is traveling to the next stage and finally coming at the output stage. So if you understand the circuit and the signal flow in the circuit, even more complicated circuits, you can break it down and understand what is going on. And then you can, when it comes to designing your own application or any particular design problem, the similar concept you can apply. You see that, okay, at some point of time, I need a very high gain, GMRO square kind of gain. So I can go for folded cascode. At some point, I may not need so much high gain. Maybe I need better bandwidth. So then in that case, I will go for the previous stage that I discussed, where you just have GMRO gain. So all these, different combinations, the basic building blocks, how it is working. Likewise, the current mirror, what kind of current mirror to use, normal current mirror or cascode current mirror or cascode with reduced swing. All these things depends upon requirement. So if you are having all those arsenals, all those weapons in your arsenal, you can attack a problem and you can use all those weapons. If you don't have the weapons, if weapon is being given to you and you leave the weapon in courtyard and then go to the war empty handed, there is no point. So you have to keep those weapons with you. These are weapons for your solving your problems. Is that clear?
Yes, sir.
Any question before we conclude? So don't get too scared if you're not understanding. Concepts are very simple. If you're not understanding, look at the basics. Go visit the previous lectures. What happened? Why? It is very simple, right? Signal flow, how it is happening, how it is getting folded, how the final signal current is coming at the output. So you can ask me in the class. You can. It's better to ask in the class, because other people, if they are having doubt, they will also get it clear. So any question before we conclude? If you have not gone through the fully differential amplifier biasing with common mode feedback, please do that. That is very important. That is also applicable to many designs. Very important topic. Common mode feedback. Please study that. You don't need, if you understand whatever is, if you go to the lecture, I don't think beyond that you will need any book, because whatever is there in the books, that is presented in a concise manner in that lecture. I don't think beyond that you need to read a lot of things to understand. Any question before we conclude? So this amplifier, if you are able to design, this will give you a much larger gain in the single stage. So today, for example, we were able to get 40 dB gain. That means a gain of 100. So with this amplifier, without much difficulty, you can understand, you can get a gain of maybe 100 into 100, or at least of the order of few thousands, because there is a factor of 1/3 also coming. So if not 10,000, at least few thousand gain easily you can get. If you optimize it further, maybe you can go to 10,000 also, or upper limit of that, maybe. So that depends upon what current you are using, etc. So we will look into that, and we will, once once you're comfortable with this Opamp, we will start looking into some, earlier also we have discussed some applications in the beginning. Probably we'll try to build on that. So one of the important things that we had discussed was the voltage regulator. So we'll try to design a voltage regulator using the Opamp that we are studying. Maybe next our target will be to get a voltage regulator design for our biomedical circuit that we had discussed in the very beginning, because we need a very precise voltage, and for that we will use our Opamp that we have designed to get a very precise well controlled voltage level, so that even if the external supply is noisy, your internal voltage to the circuits is very stable. So this will be our next agenda. So for that we are building our tools. We are building the concept of DC analysis, AC analysis, frequency response, phase margin, gain margin, Opamp circuits, Opamp biasing, Opamp small signal analysis, stability analysis. All these things will be utilized for any system. So once these tools are ready, then you can see that, okay, building an application like voltage regulator, which is a part of a bigger application, your biomedical circuit, that will become easier. So let us build our tools so that we can look at these bigger building blocks, which are part of our big system, which is our biomedical signal processing system that we had discussed in the very beginning. Is that clear?
Yes, sir.
Okay, so let us conclude. I will probably try to give you some assignment on the coded Cascode. You can read up also. I think there may be some, if I find some good PDF, I will give you. Sometimes books will give you more complicated analysis. Going through the books, it will take sometimes more time and effort than going through lectures. So that's fine. Lectures, we are trying to simplify and give things in a concise manner. In books, analysis that is also given is mostly, generally, they will try to do more exact analysis. That becomes cumbersome. So in lectures, we try to simplify and give you only that much information which is required for understanding the circuit behavior. Lot of exact analysis and derivations may not be required because they don't lead, unless there is some intuition hidden in that or some important concept in that. Exact analysis may not be so important. More important is intuitively understanding what is circuit behavior with simplified small signal analysis with justified simplification. It's not, cannot be some random simplification. With justified simplification, understanding how the circuit is behaving. And then once these tools are getting ready, then we will be able to solve system level problem. Right now you have just looked into one in first simple example, single ended amplifier you looked into was transimpedance amplifier. There you had some specification, you had some target bandwidth and gain, etc. You looked into how many challenges you had there in solving that simple problem. And then yesterday you just today we looked into another simple example, simple Opamp using a voltage follower, and we want to get a good accuracy. So we try to see that, okay, how to increase that accuracy. So all these things ultimately these strategies will be part of any bigger system. You are designing a LDO. How does the requirement for LDO come into picture? That is also coming from bigger system. That, okay, in our biomedical system, this is the requirement of LDO. This is the specification of LDO. This much ripple I can tolerate. My LDO noise should be lower than this. All that thing will be there. Based on that, you have to design the LDO. So when you design the LDO, all the analysis will come into picture. All the AC, DC, stability, noise analysis, bandwidth requirement, etc. And there are many more things like how nicely it is able to regulate, how much lower is the ripple at the output, how stable is the output, how quickly it is able to settle to the output required value. All those things will also come. So just get these tools ready. You have to be, you have to spend some time and effort to, keep your tools sharp. If you don't have the tools sharp, then bigger topics, system level topics, you will not be able to appreciate. So please put some effort on this.
So
Okay.
we get time to prepare these topics, because it's like we're getting new topics introduced quite quickly, so we need to catch up. So if possible, could we get time to prepare
just
these?
2 hours lecture and you have the whole day. What do you mean? How do you carry out your this is summer holiday, you don't have any other course, and 2 hours I'm teaching, and then also you're not able to catch up with the theory. What will you do in the semester?
Actually, we do have other courses. Actually, we're trying to do those in parallel. So if we can get more time to prepare for these, the theory.
Then these things, I want, as I told you, the agenda over here is to select people who are having some focus and who want to, work in this domain. And if you have too many other things, then probably you will eventually you will not work. Simply, you will not get aligned into the projects also. So in that case, I will not slow down for you. So I will continue at a pace where people who are dedicated, people who are interested in this topic and who want to carry out projects in this topic, they can learn fast. They can take the advantage of all the time and effort that I am also putting, and they can come to a level that they can quickly get ready for some projects. If you do 10 things in parallel, you don't have time for preparing for this, and then it will be a problem because it will slow down the whole progress, and then you will not be ready timely. So we also need to be sure that you get ready for this topics timely. If the whole summer passes and you are not ready, then what is the point? So at this stage, that is a problem that I have encountered in earlier students also. They get into too many things at the early stage. So if you have to work in VLSI, analog VLSI is a topic which requires a lot of focus. If you do not have that focus, if you get scattered into other things also at the same time, then you will not be able to do. Simple, very simple. So I have last 2 batches, I have seen students who lose patience, who are they are scattered into too many other things, and they probably uh, lack commitment, right? So mlog, any other topic that you take requires commitment. If you have to build your foundation, you need commitment at an early stage. Later you can diversify. Like as professors at this stage, we can diversify. We can do many things. I work on many other things also. It's not only IoT. I work on software also. I work on IoT also. I work on startup ideas also. But this is my core area, and this is because I have this is a core specialization. I have done my masters in this. I have done my PhD in this, and I have spent enough time on this. That's why it is my core area. So if you want to take this as your core area, then you need to spend time and effort and do projects on this in a focused manner. Otherwise, this is not a topic that you will be able to master by doing part-time engagement. That will not happen. Even when you are having semesters on, if you're working on this, we will expect that we want a team who will be sitting with us in the VLSI lab and enthusiastically pursuing interesting problems, publishing, designing chips. We want that kind of team. Chip design does not work when you are having scattered mind and doing 10 other things. I will do software also, I will do AI also. So you are here, AI everybody is doing, data analytics everybody is doing, IoT also many departments can do, most of them can do. But this thing is specialized, highly specialized. Only EE and EC people can do because they have taken those courses, they are capable of doing it, nobody else can do. So you should capture that specialization which is specially made for your department, not just doing anything which is open to whole world. So you have worked hard to come here in this department, and then you have got into nice disciplines. So still, if you want to go for something which is very generic and not specialize for something which is special for that department, then what is the point? Money point of view, there will be no difference. Career prospects point of view, equally, or I would say more prestigious, because this is a very special, I would say, skill, or very special set of people in the world who have this kind of know-how and expertise in the industry. So number of people having analog design skills is, as compared to people having AI, ML, data, if you look at it, the ratio is very, very skewed. So you have the opportunity to get into that discipline. And there are people sitting over here who are ready to, guide you, help you. So, you should think about that and spend your time and effort in building. I told you very frankly, if you do not focus on this topic, if you do not spend time, if you think that, okay, I will do 10 other things also in parallel, that will not happen. This topic needs focus, needs dedication. It needs to overwhelm your mind. That if you're talking about a particular problem, design problem, you will have to think about that problem multiple times a day, solve that problem, look at it from different angles. You have seen that simple example, right? That simple TIA example that I gave in the beginning. How much different parameters are coming into picture: input impedance, bandwidth, gain, and output swing. How to cascade, how to add multiple stages, how to make sure that each stage is controlling its own bandwidth, and it's maintaining the bandwidth. How to apply new circuit concepts to enhance bandwidth or input impedance, etc. So many things in a small circuit like that. So when you talk about a bigger system, at every point we have to take care of these issues, and it requires a lot of concentration and focus. That's why this is a very specialized area. Without focus and without concentration, you will not be able to do, whether it is learning concept or applying concept. So you should be proud of doing this. And when you come out of your when you graduate here with accomplishment in this area, having published something, having submitted a chip or designed a chip, having worked for companies, then you will feel the difference. It's not open to everybody, and anybody from the IT from all across department and come and take some courses here and there and start working. This is a topic which requires special focus. Without that, forget chip design. Simple. I myself, we work on problems where every day we have meetings, every day we are discussing problems with people all across. People sitting in Europe, people sitting in America, and we are doing projects with them. So that is it requires with those experts also. We are having daily discussions. We are having so many challenges in critical modules of the design that we need to overcome. So without focus, I have other interests, but when I work on this topic, I have dedicated time. I have to spend that much time. Otherwise, I will not be able to produce the outcome that is required. So that's why be very, very careful. If you don't have focus, then this topic will not work for you. Very simple. Okay, so I think enough of bhashan. So think about it and prepare sincerely. And already I'm thinking that I'm already going very slow. Means if I have to finish these things and prepare you faster, I should spend, you should basically try to cover these things fast. It is like a crash course that, okay, important concept being covered fast so that you can come to a certain level. Whatever I'm teaching, so many topics that I'm teaching, probably you will not even get together all these things in a master's course as well. But I'm covering this because I want you guys to be at least those who are having enthusiasm and seriousness to be prepared, and we want to maintain this. This focus is getting lost. Last few years, what we have seen is lockdown happened, this and that happened. The interest in this domain has gone down. People, they are not. I also did not basically invest much time last 2 years. So that also, I summer course also I used to take. I did not take last 2 years. So those things used to be, earlier all the professors used to participate in summer course. Maybe once we have offline, we will do that once again. Right now, I am only doing it. Gradually, we'll call others also. But for that, if you have to really work in this area, you have to get, you have to invest dedicated time and focus. Okay, so let us conclude and we will meet tomorrow. And please try to complete the video assignment and the simulation assignment that are given to you. Don't take it if it feels boring, or if it feels if you feel that it is you are stuck at some point. Sometimes I may be busy. For example, today I was throughout the day I was busy. I got free just for taking the class at 4:30. I came and I somehow 4:30, but I came here in my office at 4:45, and then I started the class. Before that, whole day was busy in some other meetings, etc., etc. So sometimes I may not be able to respond immediately to the question that you are posting, but I will try to be alert. And if you're having doubts in the assignments, whatever is given, I will try to respond right away. Okay.
Yes, sir.
Okay. Thank you.
Thank you, sir. Yes, sir.